This meeting is being recorded.
In this video, we'll continue with section 7.7 and specifically discuss now elimination reactions, E2, and their stereoselectivity. So we're asked to consider the dehydrohalogenation or removal of both a hydrogen and a halogen for 3-bromopentane. And we're told that two stereoisomers are possible products. So we're taking a look. Here's our substrate, our starting material. Here's our base. And as we're told, we have two elimination products that are found. So we're told here that we have this energy diagram of this reaction, and we are um, asked to use this energy diagram and Hammond's postulate, which I have just a short description from, listed up here in the right-hand corner, to explain why the trans isomer is formed in this stereoselective process. So what we see here with the energy diagram is that our activation energy is lower overall to get to the transition state for the trans isomer. And also using Hammond's postulate, we see that we know this is an endothermic process, so the energy will be closer to the products at the transition state, and we know that our transition state will resemble our uh, our products more than our reactants, right, due to Hammond's postulate. So what we see here is that overall, the trans isomer, which we're told is favored, has a lower overall activation energy. So this would be why this is our major product. So we can see that there are also stereo-specific reactions, not just stereo-selective reactions. And these can be specific for a few reasons. So we'll discuss about how if we have one or more beta hydrogens that can be removed in an elimination reaction. So that's one factor that we might have different sites. But this reaction here that we're shown will produce only one product. And we're given this orientation here of our hydrogen and our bromine that will be eliminated in this reaction. And we will take a look at why this product is favored over the other, why only one isomer is formed. And we're told that only the E isomer is formed. Right, so that's what we see with these two groups here. So to rationalize this, we have to consider that transition state and the CH bond shown here, and then our CBr bond that I just boxed in there, have to be rotated in the same plane as that which the pi bond is forming. So between the carbon-carbon here, of course, that would be the plane where the pi bond is forming. So these four atoms that are shown in red must all lie in the same plane. Another way of saying this is that our beta hydrogen and the leaving group must be coplanar. So that's what we see here, that hydrogen in red, and then our halogen, our leaving group in red as well. So these are called coplanar by this description. And we can visualize this a little easier if we use Newman projection. So we see our same compound that was given before, and we are told that we can rotate this carbon-carbon bond to start to see different rotamers, different conformations of this compound after rotating freely upon that carbon-carbon single bond. So we see here in this first staggered conformation that we have our halogen, our leaving group, and our hydrogen in this anti-coplanar conformation. And then over here, we see that we have our hydrogen and our bromine that would be eliminated in a syn coplanar orientation. So the reason that only one of these is chosen, one of these conformations will produce an elimination product rather, is due to the fact that this conformation is much lower energy in the anti conformation. So we will see very little, if any, at times of the higher conformation rotamers. So again, due to this elimination process, we're going to see this orientation of our products. So what we see here in this conformation, we can see drawn over here, but without our halogen and our hydrogen that have been removed. So this same orientation is what we use to visualize that pi bond formation. So what we see here is that the methyl and our tert butyl are on the same side of the double bond, and then our phenyl and our hydrogen are on the same side of the double bond. So we can see that in this Newman projection with the bromine and the hydrogen removed, and we can see it over here in that same orientation when we add that double bond. So we know that the leaving group and our hydrogen have to be what we were referring to before as coplanar, but there is some wiggle room, if you will, with the exact angle that is necessary for E2 mechanisms. We have seen through experimentation and documentation, there's evidence that anywhere from 175 to 179 degrees will be sufficient for this elimination mechanism to occur, and we therefore call this term anti-periplanar instead of anti-coplanar, just to include any of those slight deviations. So we always note that the E isomer is usually rather more stable because it's less sterically hindered. But because of this anti-periplanar requirement for elimination, sometimes the less stable Z isomer can be produced. So let's take a look here and assume that these reactions, so our substrate over here is reacting with some base, and we want to know what our elimination product will be. So we assume that these proceed through that anti-periplanar transition state. So we see over here that our R1 group and our R1 group over here are both on wedges, and we have this anti-periplanar orientation of our two groups that will be eliminated, our hydrogen and our bromine. So what we see in our product here is that our two R1s that were on the wedges are again going to be on the same side of our pi bond, and then we have R2 and R2 shown down here. They are going to be on the same side of the pi bond. They were both on dashes in our original compound. So what we see when we have our R1s on dash and wedge here is that they will end up on opposite sides in our product after our elimination. But we should still recognize the this anti-periplanar orientation of our hydrogen, our bromine, and then we follow that same process where we create that double bond, and based on the wedge and dash orientation, we can orient our R groups in our final product. So what if we look at a carbon where the, a substrate where our beta carbon has two beta hydrogens. So what we can see is that two different rotamers can exist, again, like we saw previously, and one beta hydrogen can be an anti-periplanar conformation to a leaving group, and this can result in two different stereoisomers that can result. So that's what we see here. So now we have at that beta carbon, this hydrogen is anti-periplanar to the bromine, and then we could rotate upon this carbon-carbon single bond, and then we could place this hydrogen within those anti-periplanar conditions. So again, we'll say that this reaction would be stereoselective because we can select which isomer can be a product, but it's not stereospecific because we have more than one. For an E2 elimination to be stereospecific, that's when both the alpha and beta carbons would result or begin as stereocenters. But we can see that over here, we just have 2 protons. So this is not at our beta carbon going to be a stereocenter. So again, we must review the difference between a stereospecific and a stereoselective reaction. So this first term, stereospecific, tells us that depending on the stereoisomer configuration of our substrate, we will produce a single stereoisomer as a product. So say we have stereoisomer 1 here and stereoisomer 2, we can only produce product 1 here and we can only produce product 2 here, right? They are specific based on which stereoisomer. But when we have a stereoselective reaction, a single substrate can produce 2 different stereoisomers. The first would be our major product, but it can also produce a second stereoisomer as a product, and this is usually less. So we have a major and a minor product. So let's look again at stereospecificity of these E2 reactions. And let's consider, again, the dehydrohalogenation of a compound. This time it's cyclohexane, a cyclohexane derivative, rather. And we see this leaving group is attached to a ring. Of course, since it's on a cyclohexane derivative. So in this first scenario here, we see that our chlorine substituent is axial and pointing up. And we can see in this orientation, if we draw a Newman projection of our cyclohexane derivative, we have the leaving group and our hydrogen in this anti-periplanar positioning. So we would see an elimination reaction occur with this this axial position substrate, but if it was in an equatorial position, the chlorine that is over here, we can see that we do not have a hydrogen available that would be anti-periplanar. So we cannot have an elimination in the more common equatorial positioning of chlorine, but they can occur in the axial position. So that's what this slide is showing us here. And we have another example here between these two cyclohexane derivatives, and we're asked which of these two molecules will not be able to undergo this E2 elimination and why. And we can see that this first compound, we'll call compound 1, can complete an E2 elimination because it has hydrogens shown here in an anti-periplanar orientation to this halogen, whereas these hydrogens are not in an anti-periplanar relationship to that chlorine, so this compound would not be able to have an elimination E2 mechanism occur. So this last line just reminds us when we are drawing the products of our E2 reactions, there are many factors to consider to make sure that we find all of our products and decide specifically what our major product will be. So these questions include, will the substrate react stereospecifically, or will be a stereoselective E2 reaction? So we have 1 or 2 products that are possible. will it produce several radioisomeric alkenes? So will we again have Hoffman Zaitsev products, things of that nature? So the only way to do this is to do lots and lots of practice problems, and we will continue with the next section in the next video.